Hi everybody, this is Dr. Bricker here with some information about the lab for this week. It's called Human Arm Model, and obviously we're not going to be on campus doing the lab, so I'm going to walk you through what we would have done and give you the data for the lab. So essentially this lab is about balancing torques. So the goal is to predict and to test the forces exerted by the bicep muscle at various conditions. Let me scroll up a little bit. This would have been the apparatus that we use. So essentially this is free to pivot here at the elbow joint, and we would add mass here, and there's a force probe connected here. So if this is the pivot point of your elbow, the bicep muscle is connected over here, so not quite at the elbow. So there's just a little bit of a lever arm here, and the mass is way down here at the other side. This might be a little bit better of a picture. So here's the elbow joint, that's the pivot point. The bicep muscle is connected here, and we add weight here. And in the lab we have a force probe. So when you add, so here's how it works out. You set it up like this, you zero out the force probe because you don't want to be measuring the actual mass of the arm itself. We're just going to compare the bicep force to this added weight over here, the load force. Okay, so we zero out the force probe and we add some mass to the hanger here. And then the force probe, which is connected here at the bicep, the force probe is measuring the bicep force. So you have a bicep force here and a weight here. They're not equal to each other. This weight is way out here, a big distance from the pivot point. The bicep force is here, really close to the pivot point. So you'll see that the bicep force is going to be a lot bigger than the load force. The reason is this is a small lever arm, this is a large lever arm. Okay, so initially we set it at 90 degrees, which this is 90 degrees. The angle is measured here. So that's a 90-degree angle. We add some mass, we measure the force probe, add some more mass, measure the force probe, and we get 4 sets of data, which I've included here. So this would have been adding 50 grams, 1, 2, 3, 50 grams, and kilograms 0.05. This is the added mass that you put on the hand. Now the added weight here is going to be this added mass times 9.8. So I left this column for you to fill out. So here's the added mass, multiply that by 9.8 to get the added weight. So for that added weight on the hand part, this is the force probe reading. And then we added 70 grams, 0.07 kilograms. You'll have to calculate the added weight. And here's the force probe reading. So you'll see that the force probe, which that's again simulating the bicep force, is much bigger than the added weight. So your bicep, if you think about it, if you're curling like a 1 Newton force, 1 Newton ball, or whatever you're trying to pick up, your bicep force is much, much bigger than that. We don't realize it in everyday life that our bicep force is so large. We're just used to it. The second part here, similar, but we set the angle at 60 degrees. And same idea, we added some mass. You'll have to multiply it by 9.8 to get the added weight. And then here's the force probe reading. Same thing here. Here's the added mass. You'll have to calculate the added weight, added mass times 9.8. And then here's the force probe reading. Let's take a closer look at this. Okay, so I've just kind of drawn this out. Here's maybe the bones of your arm, and here's where the added weight is. So the added weight, this is m times g. Over here at a relatively large distance from the pivot point, your bicep muscle is over here. So force bicep. Now I drew the bicep force much bigger because the distance to the pivot point is much smaller. So we know that the torque from the bicep has to be equal to the torque from the weight. So torque bicep has to be equal to the torque due to the weight. Now the torque from the bicep is the force from the bicep, that's the force probe reading, multiplied by the distance to the pivot point, so RB. And it's really small. It's just this small distance right here. I can't even draw it on here very easily. This is the distance to the pivot point for the bicep. On the other hand, over on this side of the equation, it's the weight and then the distance from the pivot point to the weight. So I'll just call it R sub W. And that's a lot bigger. That's all the way from, I don't want to make my drawing too crowded, but this distance. So this is an extended free body diagram. It has the forces, but where the forces are actually acting. So torque from bicep is equal to torque from weight. But the distance from the pivot point to where the bicep muscle is acting is a lot smaller. This is smaller, so this has to be bigger. This is bigger, so this can be smaller. And then the torques are actually balanced. So you'll see that the bicep force has to be much bigger than the weight. Okay, and then the second part, we've set this to 60 degrees. So this angle here is set to 60 degrees. So when you see the data, you'll see that the bicep force is less in this case. So the bicep force is the greatest when we're at 90 degrees. When you're at 0 degrees, there is no added torque. It's just hanging straight down. At 60 degrees, you'll see that the bicep force isn't quite as big as it is in the first part. It's because the weight doesn't have quite as long of a lever arm. So this would be the distance to the pivot point for the second part. It's not as big as it was in the first part. So in the first part, the lever arm was slightly bigger for the weight. It's nearly the same for the bicep force. It's a little bit smaller in this part, but not by too much. The distance from the pivot point to the bicep force, it's still really small. It's just this distance here. Okay, so you'll see that, when you go through and look at the data, and we'll look at it again in just a minute, that the ratio of the bicep force to the weight in the second part is not quite as big. Okay, so let me go back and look at this. We have here's the equation that you'll really be using when you take a look at this. If you try to quantify this relationship, here's what we're going to be looking at. This. Okay, so I'm going to be graphing bicep force on the vertical axis versus bicep force versus the weight on this axis, and you'll get something like this. What does the slope actually tell you? So bicep force to weight. So if I take this equation here and I want to solve for the ratio of bicep force to weight. The ratio of bicep force to weight, that is the slope. So the ratio of bicep force to weight is the slope. So let me rearrange this equation just a little bit. I'm kind of running out of room here, but I'll try to do it down here. Okay, so bicep force to weight, remember that is the slope. So I'm taking this equation, solving for this. Bicep force to weight is equal to this distance over this distance. And this is actually the mechanical disadvantage of your bicep muscle. You have to put a lot bigger force in and you get a lot smaller force out. Okay, so you're going to have to make some Excel graphs. Let me just refresh your memory on how to do that. Okay, so I'm just going to make up some data. 1, 2, 3, 4, 5. And let me just pick some points here, like 9.9. This is completely made up. I'm just doing this so you have the idea about how to do this. 29, kind of making this sort of linear, but not perfect. 42, 50.5. So if you want to make a graph of this data, and what you're going to be graphing when you do the lab is bicep force versus weight, what I'm just graphing is some generic stuff. You just grab this information, go to Insert, and then I usually use this one, Scatter Plot, pick the top left one. Okay, good. So pretty linear but not perfect. You want to put some titles on this. So quick layout, use the upper left one. And then now you see we can put titles on. We've done this in the lab before. There's only one series of data here, so I'm going to click on that and just delete it. So you can put the chart title. You'll have bicep force here, weight over here. And then you want to include the equation of the line. Remember, the equation of the line gives you the ratio of bicep force to weight. So if you right click on the data point and add trend line, there's the line, and then down here is display equation on chart. So it's in slope intercept form, so the slope is this number. And you'll do the same thing. You'll have a slope, and that your slope will be the ratio of bicep force to weight. So that's how you can quantify that relationship, the mechanical disadvantage of your bicep muscle. Okay, so to sum it up, here's the here's the handout. Here's the data. You just have to finish up the added weight, multiply the mass by 9.8. Same thing for part 2. And then here's what to put in the report. Experimental design, state the goal of the experiment, which is given in the very beginning. Describe just the basic setup so somebody has an idea of how this works. Include a drawing of this setup. Just basically something like this. Or you could actually just use this picture if you want to. And then describe what you did. Add some weight, get the bicep reading, that sort of thing. And prediction, include the predictions from section 1. You'll see that when you go through the lab. Attach your data and Excel graphs, so you have to make the Excel graphs. Analysis, bicep force versus perpendicular load. That's the first part. So include all that information. 2 down here, bicep force versus non-perpendicular load. So go through, include all that information, and then summary. So this would be the lab that we would have been doing this coming up Friday, which would have been the 3rd. So this lab report will be due on the 10th then, and you can upload it through Blackboard. So when you go to look at print out the lab, you'll see there's a spot for you to actually upload it. So you can work on it on your own, or if you have your contact information for your lab partners, you can do it as a group report as well. Just make sure everybody's name's on it. Okay, if you have any questions, just let me know, and I will talk to you soon. Bye-bye.